So today we are hosting Tania Ahmed from Macquarie University, and she's working with dust obscuration and star formation and fiber configuration. And yes, so the floor is yours. Thank you so much for visiting us.
Thank you. So yeah, as Maya said, I'm from Macquarie Uni, and I'm working my project that I'm working. It's mainly twofold. So one part is dust obscuration part that's working with Andrew Hopkins, and the other part is fiber positioning system. That's with Sam and Alice. Those are my two supervisors. And I'll be talking on actually 3 of my papers. So the first 2 papers were on dust obscuration. The other one was dust geometry. And the third that I'm still working on, haven't submitted yet. So that's on the fiber positioning system. So in the dust part of the project, we're looking at how the obscuration properties of radio sources differ from the optical parent sample that they're chosen from. We investigate here the importance of radio selection in probing heavily obscured galaxy populations. And what we are finding is that the radio detected populations have higher levels of obscuration, and we are missing the low mass, low Balmer decrement, low obscuration systems compared to the optical parent sample that they're choosing from. And we further investigate the link between the dust obscuration and the star formation rate using the H-alpha luminosities and the radio luminosities. And I also briefly mention on the tool that I'm working on for the existing fiber positioning systems. So for our analysis, I'm using both the optical data and the radio data. So for the optical part, that's coming from GAMMA. GAMMA stands for Galaxy and Mass Assembly, which is a multi-wavelength photometric spectroscopic survey covering an area of 286 square degree with 300,000 galaxy spectra across 5 sky regions. And so there are many primary goals of this survey, mostly on testing the galaxy formation models by measuring star formation efficiency, measuring the connection between star formation and stellar mass, uncovering the mechanisms of stellar content. And there's around 300 plus GAMMA papers already published with 17,000 plus citations. So it's nice to be part of GAMMA. And for EMU, EMU stands for Evolutionary Map of the Universe, with the RMS noise level of 25 microdensity, and then they're expecting to measure around 30 to 40 million sources across their survey duration. And there are 12 key science projects for the EMU, and some of the things are here, like the evolution of star formation in galaxies, massive black holes, understanding their relation to the star formation, exploring the last-scale structure or cosmological parameters, exploring the different regions of observational parameter space. And there are over 400 team members working as part of EMU from different countries. And until now, around 80 plus EMU papers got published with 1,600 plus citations. And the main motivation of the first part of this work project started by following to Afonso Hopkins et al. 2003. So Afonso explored the validity of the luminosity or star formation rate dependent obscuration at different redshift bins. And they used radio selected sample of star forming galaxies, which are insensitive to dust obscuration. But in our case, for selecting our samples, we have radio detected samples that's been chosen from optically selected galaxies. So for the data, we combine photometry from GAMMA, KIDS, Vikings, which is our GKV catalog, and cross-match that with the radio and the WISE catalog. And by combining this data, we analyzed for volume limited sample, just like the here in the slide here, which which shows us to defining our volume limited samples in different redshift beams. So I have constructed 4 volume limited samples in different redshift beams, starting from 0 to 0.35. And that's actually the basis of our subsequent analysis. And by defining that constructed sample, we are actually trying to keep our chosen galaxy sample above our radio detection limits. Our galaxy samples include both star-forming galaxies and AGNs. But as we are interested here, measuring the obscuration properties in star-forming galaxies, so we need to distinguish between these two, which we do by excluding the AGN-dominated systems using the standard diagnostic diagram, such as the BPT diagram, which perhaps is the most common method. So while there might be a possibility that we have overlooked some AGN systems solely relying on the BPT diagram, but their inclusion in our sample would not significantly alter any of our findings. So I've plotted here the full gamma sample, which is in gray in the left panel. That's using the BPT diagnostic, and the blue and the red ones are the star-forming regions, and the red ones are the AGNs. And the top right panel, I've plotted only the GKV catalog. So over here, the blue ones are the optical parent sample, and the red ones are the radio. Again, I've also plotted, using our both optical and the radio sample with the Wise color diagram, just for the purpose of illustration, because the Wise color diagrams turn out to be a good discriminator for plotting different populations. So we can see that there are 4 different regions there, like spheroids, intermediate disk, active star-forming disk, the AGNs, again, just for the illustration. For the purpose of our investigation, we use Balmer decrement as the obscuration sensitive parameter, as we are trying to understand the impact of dust on sample selection. And as Balmer decrement is the direct tracer of the effect of dust on that fraction of emission that escapes a galaxy, this is the appropriate parameter to use for our analysis. And we are aware that Balmer decrement is the ratio of the H alpha and H beta emission lines. Over here, I've plotted both histograms of Balmer decrement as well as the scatter plots. So in the left panel, we can see that the radio detected populations miss the lower end of the Balmer decrement detected populations. In this case, the least obscure systems are preferentially not the radio detected ones as compared to the most obscure galaxies. And the dashed lines here, so the horizontal ones, the vertical ones for the magnitude limits for each redshift bins. Horizontal ones is the nominal KSB value of Balmer decrement 2.86, so which means that in normal condition, the ratio of brightness of H alpha to H beta emission line should be 2.86. So that's plotting. And I'm showing, even though I've constructed 4 volume limit sample that I've shown in my previous slide, but I'm showing the tubeless redshift bins here and in the rest of my slides, because it's more visually apparent in the tubeless redshift bins. And we've plotted the same distribution in terms of fraction of radio and Wise compared to the optical parent sample, just to quantify the effect in a more visual way. And the Wise sample here seem to have similar distribution of obscuration at a relative constant fraction. But in case of radio ones, this seems to be quite different. And I'm not going to go in details to that for now. We also plotted Balmer decrement as a function of stellar mass. And over here, we can see that at the higher mass end, we are picking all the galaxies. So that the higher mass end, we're picking the galaxies at radio and Wise, as well as for the optical parent samples. But as we go to the lower mass end, we start losing the radio detected sources. And those radio detected galaxies have higher Balmer decrement compared to their optical parent sample. We have also used galaxy main sequence or star formation rate stellar mass relation to quantify the effect, to explore the effect of our radio sensitivity limit. So over here, I plotted star formation rate as a function of stellar mass. I've also color-coded that by Balmer decrement. And just like in the previous slide, we start losing the lower mass population from the radio detected sources compared to the optical parent sample. And those radio detected ones that we are losing that have lower levels of dust as traced by the Balmer decrement, corresponding to low star formation rate, low metallicity systems. And we have also defined an empirical threshold for the star formation rate limit. So, and if we exclude the galaxies below this threshold, our results remain unchanged, which is why we have reproduced the fractional figure again, and that remains unchanged compared to what we've done. And that implies that those lack of low star formation rate, low obscuration systems that we're missing is not a consequence of our radio sensitivity limit. And we further try to explain why this might be the case using the stage galaxy formation model by Nuiske et al. 2007. So this model by Nuiske explains how galaxies change over time in terms of star formation. It assumes that high mass galaxies start forming stars in the earlier universe, but the star formation slow down quickly, while the low mass galaxies start their forming stars later state, but continue doing so for a longer time. So, and this is also known by Covey et al. 1996, commonly known as galaxy downsizing. But this model does not explain our results, but it sets the scene for why low mass galaxies seem to be different for their high mass counterparts. Another effect we have added is the leaky box model. And in case of leaky box model, it's mostly like low mass galaxies have small potential veil, and the cosmic ray electrons that are responsible for the radio emission can more easily escape, which means the radio emission is lower than otherwise expected. But the leaky box model is mostly mass dependent. So by itself, it does not explain our results either. With that in mind, we added another explanation with the possible variation in IMF or initial mass function. We are aware that radioluminosity from star formation is associated with high mass stellar populations. It's the high mass stars that produce the supernovae, whose ejecta accelerate cosmic ray electron population to produce synchrotron emissions at radio wavelengths. These high mass stars also have higher levels of obscuration. So now, if there are fewer higher mass stars present than expected, radioluminosity will be lower than expected. So our result of low mass, low obscurations systems could be a consequence of IMF being poorer in low mass stars, poorer in high mass stars compared to their higher Balmer decrement counterparts. And this speculation is qualitatively consistent with the results that we see here, as well as analysis done by others, such as Gunawardena 2011. They found that low mass, low star formation galaxies tend to have IMF lacking in high mass galaxies compared to their higher star formation counterparts. So also some other results done by Lee et al. 2009, Baseli et al. 2009, then Mirror et al. 2009, Nanayakura et al. 27. Those are relatively consistent with our approach. So following these results, we decided to look in more detail at the obscuration properties using the same sample. So we again constructed the sample But in this case, instead of choosing the absolute magnitude limit as we adopted in our previous work, we used stellar mass limit for our volume limited samples here. That's I'm showing in the left panel here. And in the right panel, we plotted dust mass as a function of stellar mass for the star-forming galaxies here. And we use measurements of dust mass for measurements using from prospect to obtain the dust mass here. Excuse me. And the reason for showing this image is mostly that, just like in our previous analysis, we are losing the radio detected samples here. I mean, there are fewer radio detected sources here compared to the optical parent sample as we go to the lower mass end. And for the remaining of our analysis, we rely only on the radio data for our star formation rate calculations. The motivation of this work started by Hopkins et al. 2001. So Hopkins demonstrated that the discrepancy between the star formation rates obtained from the H-alpha luminosity compared to those derived from the radio luminosities. And in their case, it's more pronounced at the highest star formation rates. And following to that, we compare the star formation rate measurements using our data derived from the radio as well as the H-alpha luminosity. So in panel A, we are plotting the star formation rate comparison, but in case for the uncorrected H-alpha, and the panel B is for the corrected after the Balmer-Dekman correction to H-alpha luminosity here. And in panel A, we can see that there is no Balmer-Dekman gradient here before the correction. The correlation is tighter here. However, the correlation shows the deviation from the one-to-one line, which increases with higher star formation rate. After applying the correction, there is a trend in Balmer decrement there, which is due to higher Balmer decrement points increasing the H-alpha. So for the higher Balmer decrement points, there's higher Balmer decrement points with the increasing H-alpha star formation rate, but decreasing with higher radius star formation rate, which shifts the lower Balmer decrement points slightly upwards, and higher Balmer decrement points goes through more significant shift originating from the either end of the distribution. To explore further the origins of these Balmer decrement variations that we see here, we assess how Balmer decrement correlates with the ratio of the two star formation rate measurements here. Rather than using star formation rates explicitly, we instead use underlying luminosity measurements for simplicity. And it's through that luminosity ratio that we consider the concept of H-alpha deficit. So H-alpha deficit is the ratio of the radio luminosity and H-alpha luminosity. And here in panel A, that's before correction to the H-alpha. So plotted Balmer decrement as a function of the H-alpha deficit, the ratio of the two luminosities. And we can see that there is no clear relation here, any apparent here. But after applying the correction, there is a tight correlation there, which is due to high Balmer decrement points increasing the H-alpha, which shift the H-alpha deficit to the left, thereby inducing the correlation. This also arises that Balmer decrement due to Balmer decrement providing insufficient correction to the H-alpha luminosity in the presence of optically thick dust. Also, Balmer decrement correction alone do not fully correct the discrepancies between the H-alpha, uncorrected H-alpha and the radio. I plotted the same distribution in 4 redshift bins. And again, I'm showing the 2 lowest bins here. And there is a Balmer decrement dependence here. And as redshift increases, there are higher masses in higher redshift bins. So following these variations in Balmer decrements, we tend to focus on how to resolve the discrepancies that we see. And we try to do that by introducing some new parameters, incorporating some dust parameters to it, specifically linking the Balmer decrement and the dust mass. And from Calzadi et al. 1994, they explored a sample of star-forming galaxies by applying different models for the geometrical distribution of dust. I'm not going in details to any of those models now. But what we have done following to that, we tried to present 2 extreme versions of the dust geometry model. So in the left-hand side of the figure, there's the upper panels are for the foreground screen dust geometry model, and the lower ones are the distributed dust geometry model. So from A to C, if we move, we can see, and the foreground dust geometry model mostly assumes that all dust lies in a screen between the observer and the stars. So if we move from the panel A, it's more like when there is low dust mass, low Balmer decrement with low obscuration. And as we move to the panel B, that case is mostly for mid to higher dust mass with increased obscuration. And the panel C is mostly higher dust mass with increased obscuration, where any starlight is completely obscured. The same thing we have tried to plot using the distributed geometry with low and then mid to high dust mass, and then the higher dust mass with completely obscured obscuration of light using the distributed geometry model is mostly all the dust and stars are mixed together. And what we did next is that as we are trying to link Balmer decrement and dust mass, so for the overall distribution of Balmer decrement as a function of dust mass, we tried to just represent where these models will get located within that particular distribution, just in a quantitative way. And next, using our data, we tried to plot the same distribution. So I plotted here both the optical parent sample and the radio sample for the Balmer decrement and dust mass distribution. And well, the horizontal dashed lines, that's the Balmer decrement nominal KC value of 2.86. And the dotted line, that's the empirical envelope line that we have defined at the highest point. So this one, the empirical line mostly traces the upper limits of the data. And this figure shows galaxy obscuration over the entire range of the measurable Balmer decrement at the higher dust mass. Right, and just like in the previous figure over here, at the lower mass end, that's where the low dust mass, low Balmer decrement, low obscuration would lie on. And as you move to the higher end, that'd be higher dust mass, higher Balmer decrement with increased obscuration. Right, so as we are trying to link the Balmer decrement and the dust mass here to introduce our parameters, I have mentioned in my previous slide that Balmer decrement alone cannot fully correct the discrepancy that we see between the star formation rate comparison figure that I have shown, and we try to use this to introduce our new parameters, try to use those ideas to introduce our parameters. Also from the H alpha deficit figure, there's a Balmer decrement dependence there. If I go back to that, there's a Balmer decrement dependence there, as well as stellar mass dependence. So there is a Balmer decrement dependence there, as well as stellar mass dependence. So combining these ideas, also this whole Balmer decrement stellar mass dependence, that kind of implies that there is a parameter that relies on both Balmer decrement and the dust mass. And we try to link these two explicitly by introducing two dust parameters, H dust and F dust. And I've added the equations here, and Balmer decrement here is the optical depth parameter. So H dust here links the Balmer decrement and the dust mass to quantify the dust geometry. Excuse me. And this new parameter is defined in such a way as to account for the optical depth of the dust. Yeah, when investigating the variations in H alpha and radio star formation rates. And F dust, that is the fractional distance between the Balmer decrement 2.86 and empirical, the defined empirical line that we have. That's what it is. We now return back to the H alpha concept again, but we're trying to show how our new dust parameter, one of the dust parameter H dust behave with this one. So we have plotted the H dust as a function of the H alpha deficit. Deficit is the ratio of the radio and the H alpha luminosity. And we can see that the correlation here is significantly tighter compared to the correlation we have seen in with the Balmer decrement and the H alpha deficit, which implies that H dust is directly associated with the dust geometry or the optical depth of the dust. And we have plotted the same figure in different redshift beams as well. And there is no systematic change in redshift here. So in a way, there is no redshift evolution here that we can see. There is a stellar mass dependence is removed, even though there might be some residual dependence still present. So next we model this relation with just using a line fit, and yeah, using line fit we do that, and then rearrange that one to get an expression for the radio luminosity. And if we use this expression with the known values of H dust and H alpha luminosity, we can estimate a predicted radio luminosity, which can be considered as a refined estimate of H alpha luminosity, or hence H alpha star formation rate. So with that, I've plotted the same star formation comparison that I've shown at the beginning of this part of the analysis. But in this case, the panel A is, so that's the updated comparison between the radio and the improved H alpha star formation rate. And over here, it's the after the Balmer decrement correction. So both the figures after Balmer decrement correction here. And we can see that there is no Balmer decrement dependence here anymore. So that's removed. And then in the panel B, we try to compare our improved version of this comparison with composite star formation rate calibration from Kennicat, so Kennicat et al. 2009 and 2012. And the correlation is significantly tighter as well compared to the previous star formation rate comparison that we have shown. So I'm just going to summarize this dust part of the project. So it's mostly started with radio detected sources that's been chosen from optically selected galaxies. And the main idea was to explore the degree of obscuration of star forming galaxies based on Balmer decrement. And we found that we are missing the lower end mass end of the radio detected population. So lower mass, low Balmer decrement, lower obscuration galaxies from the radio source, so we can't detect those. And it's still a puzzle why that might be the case. We try to explain it with different models and still puzzling. And then we started exploring further, trying to link Balmer decrement dust mass and defining two different parameters, H dust, F dust. And the intention was to find a way to improve, define and improve estimates of H alpha luminosity and hence H alpha star formation rate. And also testing with or checking with a physically motivated approach like the Kennicott's one, which implies that our approach is consistent with established methods. And using our approach can also be applied, implemented in the absence of the radio or the far infrared data, having Balmer decrement, dust mass, and H alpha should be sufficient to obtain that improved estimates of star formation rate. Right. Now I'm just going to talk briefly about the other projects that I've been working on. So that's on fibre positioning system. So it's mostly, I'm working mostly on a tool that's designed to model the functionality of the current fibre positioning system. So like the Starbucks or the tilting spines or the theta phi. And so it's mostly like the parameters that we have. So it's more like through a systematic systematic analysis of both the observational as well as the instrumentation parameter space. The tool can assess the efficiency and the completeness of a system. So across multiple visits or observations. So I've been testing that, and I've mentioned some names like for Starbucks, Phobos, or Fibre, Foremost, because those are the parameters I need some parameters. And when I'm saying the parameter space, that means like the target density, field of view, those kind of things, or control radius, exclusion radius. I need for my fiber position, I need a home position for my fibers, so defining that, and then testing separately, tested those. And then there is a plan for the WST, wide field spectroscopic telescope. And there is already a design concept on a new fiber positioning system on that one. I haven't tested that one yet, but I will soon. I have to start doing that. Yeah, so it's mostly that. But I'm not going to talk about how the tool is working or what sort of algorithms I'm applying, or I would not reveal at this stage because it's still a work in progress on that one. But I just wanted to show that how this is at least in more generic way. So this is just the first 3 visits, or if we say first 3 observations. So that's the very first one, the way the fiber is trying to allocate for a certain target density. And then the second visit and third visit, we started allocating fibers to those targets. So mostly that and so on. And at least for now, it's mostly 3 to 5 visits. It's enough for allocating all my fibers. Yeah, and then around 95, I think 95, 98, depends on the type of the system. So around 98% completeness. But again, there's so much work to be done here. So I'm still at the early stage, I would say. So yeah. Yeah, that would be all. Yeah, thank you.
Yes, thank you so much. So do we have any questions? We do have time for questions. Yes, first.
Yeah, like Gandalf from Lord of the Rings, not all that glistens is gold. Your H alpha, are you sure it's all coming from star formation that can have email shock taken? So I suspect okay, can't be solid. Otherwise, lovely talk.
Thank you. Thank you for your comments. Yes.
Yes, sir.
So I was wondering if you've thought through what your different scenarios for explaining the lack of synchrotron from the lower mass star formation rate part of your sequence would have for the FIR radio correlation, right? Because that's another observational constraint that you have. So I'm wondering if you've thought through, I mean, right, the FIR, there is an FIR radio correlation. The slope isn't exactly 1, it's like 1.1. Have you thought through how, are any of the scenarios you proposed consistent with that or inconsistent with it?
We haven't included that for analysis, not at this stage. So, yeah.
You might think some about that and whether some of your explanations will run into problems. Some of your,
Okay.
right, could that be a way of basically, you have these 3 possible explanations. Can that be a way of differentiating between them? Some of them imply deviations from the FIR radio correlation or slopes that aren't convection.
Okay. All right.
Do we have other questions? Yes, Andrew?
I should probably know this as a co-author, but did you look into inclination, like the galaxy inclination, as if there was a dependence?
We did look at, and there's not much, I think around 3% of our sample includes the inclined galaxies. So yeah, that 3%, including those, might not be that much significant for analysis. So that should not affect significantly at all, I guess.
Great. Tim?
I'm also wondering if you try laying, for example, on right.
No, we
And
haven't.
also, have you ever tried to become those
No, we haven't done that. No, that bit, yeah.
Sorry, maybe I will just reiterate, because I'm not sure if Zoom people heard that question, but it was about decomposing the radio spectra to use just the thermal component.
Mm-hmm.
Right, I saw a question from Bailey.
Thanks for your talk. I was wondering, you had some plots with the Barber decrement against the luminosity ratios. I was wondering, sorry if I missed it, what the correction was that you applied before and after that left you with that.
What do you mean? Correction to the H alpha luminosity?
So there were plots, it was the log Barber decrement on the y-axis. These plots here. I was just wondering what the correction was between plot A and B that you applied.
Yeah, the correction to just correcting the H alpha luminosity, that would be the uncorrected one.
Right.
And the B is after correcting the H alpha luminosity, applying that correction. So.
And that's correcting for. So you're correcting the H alpha luminosity.
For the Balmer decrement that we are trying to obtain. Yeah.
All right, so, Marcus?
Sorry, let's throw one more just idea that occurred to me.
Okay.
I wanted to see if you'd thought about it regarding going back to the correlation with the radio. So another effect that it seems to me can be important here. So you talked about a leaky box, right? Maybe you're not capturing all of the electrons. It seems to me like a potentially, I would guess most galaxies are electron calorimetric. You can't have electrons escaping into the IGM thing. But what you could have, and maybe this is important, is the portion of the electron power that's radiated into synchrotron versus inverse Compton. can depend on the magnetic field strength. So I'm wondering if the source of your correlation is that galaxies that don't have much ISM, or the ISM is very thin, which don't have much Bomber-Decker, therefore, also don't have very strong magnetic fields, right? I mean, the strength of the magnetic field should scale somehow with like the ISM pressure. If you've got a weak magnetic field, you don't get much synchrotron emission because all of the electron power gets dumped into inverse Compton. Whereas if you've got a strong magnetic field, more of it goes into synchrotron and the galaxy's radio bright. So it's just an idea I'm throwing out. I don't know if you've thought about this at all. But this,
I think there was a similar sort of idea when I was working through it, but then my supervisor said, no, we have to put on hold to this one and to the next one. So we kind of tried to keep it to that for that explanation, and then we'll come back to that one, I guess, in the next bit.
Because that strikes me as a lot more plausible than saying that you're losing that you're losing electrons. I mean, it's I'm very skeptical of the idea that you could be leaking electrons into out of the galaxy just because the electron loss times are usually so small. No, I think it was leaky. I think it was a leaky.
Okay.
But so you might not be leaking them out of the galaxy, but you might be leaking them out of the synchrotron channel and into the inverse Compton channel.
Okay. Right. All right.
There just may be fewer low Barnard-Eckman AGN dominated
spectra there.
because they're intrinsically inclined without us.
Mm.
So you won't see many AGN dominated ones. You'll see more 3, 4 as the bottom end of the AGN.
Right.
That's why it's stronger further up the AGN branch. You get stronger than that. It's completely dominated by non-H2.
All right.
Right. So a last question, maybe. So we are going to be heading for lunch at Masala Hut, and as always, we have spots for 5 students. So let's meet at 12:30. Sorry, not 12:30. At 12. And if you want to talk to Tania, she will be here the whole day. I have sent the spreadsheet where you can sign up as well. So yes, let's thank our speaker again. Thank you so much.
Thank you, Maya.
Maya,
of course.
Yeah.
This is the most important part. So here's the wine.
Thank you. Thank you.